Okay, this is our third section on dynamics. We're going to talk a little bit about Newton's law of universal gravitation. Um, one of the big problems, this is one of the big problems that Newton solved, and we'll talk about it a little more when we get to astronomy. He was trying to figure out why planets move in ellipses and in elliptical shapes, and or conic shapes, I should say, circles, ellipses, parabolas, hyperbolas. Um, Celestial objects follow those paths, and he was trying to find an equation that would, for the force of gravity, that would give rise to paths like that. And so it was a very hard problem, and he had to sort of come up with calculus to figure out how to solve it. But he did, with some help from, at least some encouragement from some of his colleagues. So the expression he came up with gave a gravitational force between any two masses m1 and m2 separated by a distance d. Newton determined that the formula for the force between these two masses was given by this Fg equals g times m1 times m2 over d squared. Well, let's just talk about what these are. Newton said, okay, the force is going to depend on the distance between the centers of the two objects. It's really the centers of mass of the two objects. M1 and M2 are the masses of the two objects, and G is the universal constant of gravitation, a property of the universe. Its value was first measured by a guy named Henry Cavendish in 1791, and it's 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. It's been measured more precisely since then, but that's a good round number for it, or a good number for it. And so this G m1 m2 over d squared is the force of gravity between any two objects separated by a distance d, and one having mass m1 and the other having mass m2. And it turns out, I can have this m1 could be the Earth and m2 could be the moon, or m1 could be the Earth and m2 could be me, or m1 could be me and m2 could be you. And d is the distance with those respective objects, between those respective objects each time. If you're looking at something sitting on the surface of the Earth, the d is the distance between the center of that object and the center of the Earth. So it's usually just used to be the center of the Earth. It doesn't matter. If I'm looking at the force on me, if I include the 1 meter distance from my feet to my belly button, because the other distance, the rest of that distance is the radius of the Earth, the distance from the center of the Earth to its surface, and compared to that, the distance from my foot to my belly button is negligible. And so you can just use it for objects near the surface of the Earth, we always use just the radius of the Earth for this number. There are different numbers for other objects, like the distance between the Earth and the Sun, or the Earth and the Moon, or a spacecraft and a planet it's near, and so on. If the masses are in kilograms and the distance in meters, then the force of gravity comes out in newtons, which we discussed earlier. A newton is about 1/5 of a pound. So this is an expression, a picture, I guess, of the force of gravity. M1 here could be the Earth, and M2 can be the moon. The distance d is the distance between the centers. Notice that they each have the same force F acting. Right, the force of this guy on this guy, or the force on this guy on this guy, since it has the product of both masses over the square of the distance between them, it comes out the same, no matter which one you're talking about. The moon pulls on the Earth just as hard as the Earth pulls on the moon. I pull on the Earth just as hard as the Earth pulls on me. So let's look at this from a sort of a mathematical standpoint. We can learn some things there too. Right? Notice that the force of gravity is inversely proportional to the square of the distance between the two objects. At the very least, you should know that as a denominator gets bigger, a fraction gets smaller. 1/4 is smaller than 1/3. 1/5 is smaller than 1/4. 1/10 is smaller than 1/5, and so on. As the denominator gets bigger, the value of the fraction gets smaller, and so as two objects move farther and farther apart, their gravitational force between them gets weaker and weaker. This is what we expect to happen, right? Because we don't see ourselves or objects flying off the surface of the Earth towards the sun, even though the sun's got a much greater mass. The distance is so much larger that the force due to the Earth on us is much greater than the force due to the Sun on us. But we could use any two objects in the distance between them here. The gravitational force is proportional to the product of the two masses. So the larger the masses are, the greater the gravitational force between them. Either or both. The force between you and me, which we'll calculate an example of that sort of thing in a bit, is different than the force between me and Jupiter, say, or something like that, right, if we're the same distance apart. Usually the gravitational forces, we'll see in a little bit, is small until objects start getting, one of the objects at least starts getting to be the size of a planet or so. And so we can ask the question, what's the gravitational force between two people, each of a mass 100 kilograms, standing 1 meter apart, right? And so here's our formula. We just start plugging into it. That G is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. You can set aside the units for the purposes of this discussion if you want to. The two masses are the same. We said they're each 100 kilogram people. And so 100 kilograms times 100 kilograms, 1 meter apart, that's my D, right? And so 1 meter squared, we'll assume that's the distance between their centers, right? If you multiply all this out, well, just this little fraction here is 100 times 100 over 1, which is 10,000. If you multiply 10,000 by 6 times 10 to the minus 11th, you get 6.67 times 10 to the negative 7, and that's newtons. And if you break that number down a little bit, it's about 6.67 10 millionths of a newton. Recall that a newton is about a fifth of a pound. So this is a few 10 millionths of a fifth of a pound. So you can see that the gravitational force between people is extremely weak. This number here is extremely small, right? This is 66 billionths, right? And so it's only when I start getting large numbers over here that the force starts to matter. The gravitational force between human-sized objects is extremely small. Only when enormously massive objects like planets are involved does gravitational force become significant. So then we can ask the question, okay, so let's get a more massive object. What's the gravitational force between me and the Earth? Well, we've done that already, right? We said, look, the force between the Earth pulling on me is mg. M is my mass. We'll say it's 82 kilograms. And g is this acceleration of gravity we came up with in the last section on kinematics, which is 9.8 meters per second squared. If you multiply those out, you get about 800 newtons. But we can calculate this another way. We can calculate it using Newton's law of universal gravitation if we know things like the mass of the Earth and the radius of the Earth, which are down here in the discussion here. And so the mass of the Earth, it turns out, is 6 times 10 to the 24th kilograms, and the distance from the center of the Earth to me, which is really just the radius of the Earth, is about 6.37 times 10 to the 6 meters. If you plug all that stuff in again, you also get about 800 newtons. It's no accident because we measure this value, and this value is what's produced by this equation. So let's sort of break that down a little bit. So how are these two forces, Fg equals mg and Fg equals gm1 m2 over d squared, connected? We said that both of these are the force due to gravity. And so if we evaluate gm1 m2 over d squared, where m1 is the mass of the Earth, we'll call it m sub e, and d is the radius of the Earth, we'll call it r sub e, right? They should give the same answer they should give the same answer as F equals mg, provided the object the Earth is acting on is the same, so m2 is equal to m. And so we've replaced in this top equation m1 with the mass of the Earth, d is the radius of the Earth, and m is my mass, which is the same m as is over here. And so our force of gravity ends up looking like this instead of like this, right? And you get this quantity in curly brackets if you break it down algebraically a little bit and you pull the m out. Well, it turns out this quantity in curly brackets, if you evaluate it, it's just 9.8 meters per second squared. That's the thing we call little g. And so So these two equations are connected by the fact that at the surface of the Earth, we just evaluate this quantity, which works for every object at the surface of the Earth, because g, the mass of the Earth and the radius of the Earth squared, doesn't change for objects at the surface of the Earth. The mass of the Earth doesn't change, the radius of the Earth doesn't change, because we're talking about at the Earth's surface. And so this quantity gives us the 9.8 meters per second squared. We call that little g, and then we use this very top equation at the left here for objects at the surface of the Earth rather than this more complicated form. Since we don't need to, everybody's going to have all those numbers be 9.8 meters per second squared. This sort of shows that you can evaluate this quantity in curly brackets, the thing we call little g, for other planets. You could put the mass of the moon there and the radius of the moon, or the mass of Jupiter and the radius of Jupiter, the mass of the sun and the radius of the sun, and you would know little g, the acceleration of gravity, that's 9.8 meters per second squared on the Earth, on those other objects. And so we can evaluate it on the moon. Instead of having the radius of the Earth numbers in here, you plug in the mass of the moon and the radius of the moon, which are given in this equation, right? And you get the acceleration of gravity on the moon is 1.6 meters per second squared. It's about 1/6 of what it is on the Earth, which means on the moon I would have mad ups. I would be a good jumper on the moon. So the acceleration of gravity on a planet or moon or any object depends on its mass in this term here and its size in the denominator. As the mass of the planet gets larger, the acceleration of gravity gets larger. As the radius of the planets gets smaller, the acceleration of the gravity gets larger, right? If m gets smaller, little g gets smaller. If m gets bigger, little g gets bigger. If r gets bigger, little g gets smaller. If r gets smaller, little g gets bigger. Those are just sort of fraction ideas, right? Fraction arguments, arithmetic arguments. Objects with very large mass and very small size have the strongest gravity. You might have heard about things like neutron stars or black holes. These are objects with enormous mass and extremely little size. And that's why things can't escape from them. A black hole, you can't escape from without traveling at the speed of light. And so that's why it's called a black hole. It's so hard to escape from it. Its mass is so concentrated. So let's circle back and talk just a minute about Newton and his equation. He was trying to relate the apple versus the moon. And so he drew a picture very similar to the one you see at the right here. And he said, look, first of all, if you just drop an apple, it'll fall straight down. And that's not too interesting. But what if you throw it out a little bit, right? If you just shoot it horizontally off at some velocity. Well, if you don't throw it too hard, it'll just arc to the ground, right? So it'll leave your hand going horizontally, but gravity will cause its velocity in the vertical direction to increase, and eventually it'll crash to the ground, right? So instead you throw it a little harder, right? And eventually you keep throwing harder and harder. Eventually you can throw it hard enough. So as gravity changes its direction, changes its velocity, right? Remember, an object that's being thrown is only being acted on by the force of gravity if we neglect air resistance, right? Assume we're in space. And so the force of gravity causes it to accelerate. In this case, it accelerates towards the center of the Earth. And if the Earth is curved just right and you throw it just hard enough, it will constantly change its direction so that it falls in a complete circle around the Earth and ends up, or around whatever planet, and ends up back where it started from. Let me see if I can just draw a little picture of this for a second. So if this is my Earth here, right, I'm just going to draw what they said there, right? And I'm throwing an object this way, right? There's this V naught. Well, gravity, as it's going, gravity is pulling it this way, right? And so what gravity does is gravity just changes the direction of its velocity each time. It wants to keep going. If gravity weren't acting on it, in each of these cases, if there were no gravity, it would just do this, right? Or if I had a switch in here where I could turn off gravity at any instant, the object would just keep going in its direction, right? An object in motion remains in motion until acted on by a force. But because in each of these cases, right, gravity is acting, it's constantly turning the object so that it's, I'm trying to draw these directions. So this is the force of gravity in each case, right? Right. And it's constantly changing its direction so that it ends up going around in a circle like this, if it's thrown at just the right speed. It has to be thrown hard enough so it doesn't hit the earth. If it's thrown too hard, it can escape completely. It can run off somewhere. And so instead, if you throw it at about 5 miles a second, that'll allow it to just go all the way around the earth and never actually hit the earth. In low Earth orbit, the speed is about 5 miles a second. So here's some questions about this. When a NASA spacecraft is launched, what happens to the gravitational force on it as it moves higher? Or, two planets A and B have the same mass, but B has a larger radius than A. Which has a larger acceleration of gravity, little g, or are they the same? All right, you should be able to answer that. Is the Earth pulling harder on you, or are you pulling harder on the Earth? If gravity exists between all objects, why don't people crash into each other as they walk past? How is a falling apple similar to the moon orbiting the Earth? Why is the acceleration of gravity on the moon different than on the Earth? All right, that's a little bit about gravity. Gravity is going to come up again when we talk about the motion of the planets and spaceships and stuff like that in the astronomy section.